Martin, can you hear me?
Looking for any bulls. I'll be nice. Yes, I can hear.
Perfect. Perfect. Okay, so I've been trying to. All right, so I got some points down that I heard. I don't necessarily agree with, but I'm curious what you would think.
Yeah, go for it.
So, can you hear me right now?
Yeah, dude.
So, for my first one that I've read about was drug discovery and molecular simulation. Apparently, I don't know how true this is, but I've heard that quantum can help with faster, drug discovery and, because it's obviously with when you're like quantum computing apparently has the capability of factoring massive numbers, and that can also be used to because it's quicker processing times for that apparently can be used for drug discovery.
Yeah, so factoring numbers and drug discovery are two different things, obviously. We don't do any factoring numbers is only relevant in cryptography. There's no other field that ever uses factoring numbers. Um, on drug discovery, well, how should I put this? When you are discovering a drug, right now you can computationally model drug discovery pretty well. There's a company that sells software that does this called Schrodinger, but Schrodinger only has 100 million in revenue, and they've been the market leader for a really long time. So it's very hard for me to imagine why this would be an interesting market if Schrodinger, who is the 800-pound gorilla in the space, sells state of the art drug discovery software and it only sells 100 million in revenue. I can't imagine any improvement would be anything but marginal because the estimations that just the regular sort of physics force field and Coulomb interaction estimates kind of give you, they're pretty good. They concur pretty well with experimental results. That's why AlphaFold is pretty good as well. So adding quantum to that may make it a little bit better, but it's like going from a 95 out of 100 to a 99 out of 100, and that's kind of at best. And it's a market that's really small. So I'm not sure we need quantum computers for this. Um,
Because I've heard about things like alpha fold and protein folding predictions. Is that, any sort of relevancy when it comes to quantum computing?
yeah, that's what I just said. That you could potentially go from, if you have an amino acid sequence and you want to predict its fold, we were at sort of 90% accuracy or whatever. These are arbitrary units. Um, Relative to the gold standard, which is X-ray crystallography, right? Now, X-ray crystallography is laborious. You have to set up experiments. You have to use beamline. It's not fun. Some proteins can't be crystallized, But at the end of the day, X-ray crystallography isn't that expensive, um, and it's still done, for obvious reasons. It sort of reflects reality pretty well. Um, so if we go from 90% to AlphaFold, which uses machine learning, not just physical laws, but machine learning to determine protein structure. That's maybe a little bit more accurate at 95%. And then the gold standard is the real McCoy is 100%. Maybe quantum gets you to 99% or something. And that I'm being generous to illustrate the point, which is let's say it gets to 100% or 99%. What's the benefit? Well, drug companies would start to integrate it in their drug discovery routines, but drug companies already only spend 100 million on drug discovery software. They're not going to all of a sudden start spending billions. Um, Nor are these companies going to be the ones to make the software. There's a lot of these efforts around, and I just don't think you need a quantum computer because a lot of drug discovery optimization happens in the lab, and quantum can't really help you there. And obviously, it can't help you with any clinical trials. So the little part of medicine that's drug discovery software, it's just such a small field, and to upgrade to a quantum computer for millions and millions of dollars when I could just click a button on my GPU and do it for free, it's really hard for me to imagine, that being worth it.
Plus, it's a small market share, and I can see that being not a really exactly a great bull thesis for quantum bulls. But what do you think of like finance and risk modeling? So like, faster Monte Carlo simulations, or optimization of portfolios, or credit scoring, fraud detection. Like I've heard all these big buzzwords, and I'm just curious what your thoughts are on those things.
Yeah, so we're getting back to another problem that also applies to drug discovery, which is where do you load these variables? So right now, it's extremely hard to even the machines don't have the storage capacity, so or the throughput. So just to put in the chemical descriptors of like protein and its state is very very tough to do, and you would have to sort of keep that in a separate state and then sort of spoon feed the calculations to the quantum computer. But you'd still ultimately need to put in lots of coordinates for the many body problem, and it's just very hard to do. So the same thing applies to Monte Carlo, where okay, if I have 8,000 stocks and I want to run a linear, approximation on those stocks, a linear combination of factors, great, but how do I do that without loading all the weights in somewhere? So it ends up being this really difficult problem. Um, and what I think the real quantum scientists, and I talk to a lot of them, are excited about is, can I get you know a and our Asanu is making a point here on the chat. Can I get a um, can I get these things to do anything? Right? Can I factor a number? Which is like this really elemental thing. And then we could worry about use cases down the road. But for now, you know, just getting it to factor a number, which is like intractable, that's really exciting to computer people. It's exciting to physics people. It's really thrilling. But the idea of like doing financial Monte Carlo on these machines is like more science fiction than reality. That's probably 50 years away. Um, just getting, just solving a 300 digit RSA, that's still, kind of out there. And again, if we can see that in 5 or 10 years, I'd be impressed. I do think it's going to happen. Um, I want to stay on the forefront of this for somewhat obvious reasons I've discussed in the past. I very curious how this progresses, but so far we're a pretty long ways away, and 5 to 10 years is kind of ambitious because we still have a lot of errors to deal with. So just putting in a 300-digit number is how many bits? Does anybody know? How many bits is that? Shouldn't be too hard to figure this out, right? Let me ask ChatGPT. How many bits do you need for a 300-digit number? This is like Ted Cruz. Okay, 1,000 bits. So right now, there's no computer with 1,000 qubits. So you need the number in memory, you need the program in memory, and you need room for like ancilla bits and stuff like that. So I'm not short circle, but what the fuck? This thing's
What are
crazy.
your thoughts on like logistics and optimization? So obviously, like you've mentioned, like the traveling salesman problem. I don't think those companies are going to spend billions of dollars, but do you think that there is any sort of leeway as things get cheaper to produce, whether it's the quantum computer or, you outsource, cloud space? Like, is there something that can be used in terms of like, is there future in this?
Yeah, I mean, so right now, there's no quantum computer that can do any of this stuff, but assuming that some of these problems are solved with fidelity and RAM and stuff like that, getting bandwidth to and from the processor, the QPU, um, you know, there's a lot of data that goes in those calculations that constantly needs to be like changed slightly. Um, and right now, like the bandwidth to and from the chip is very slow. And in fact, the chip's calculations are quite slow too. And recalibrating the chip for new calculations is really painful. So it's going to be hard to get these things competitive because even if they can do the problem faster? Well, the approximations are very fast on silicon, and they can basically just, they're instantaneous, and you don't need to reset or error correct or recalibrate, ions in space. You just go. And, that's the power of silicon. But of course, there are some powers of quantum too. So, I think that it remains to be seen. It's like very speculative, but I will say that like Jensen has said, he said on the quantum day at GTC, he specifically sort of sneered at uh, the issue with traveling salesmen. He said we have great approximations. We don't need more approximations to traveling salesmen. And again, I think that, can I see a future where 30 years from now we figured out how to put gigabytes per second of bandwidth on a QPU, and we figured out how to calibrate instantly, and we figured out how to do all that stuff? Would some work move there? Absolutely. I think that one of the problems is I'm not sure that day will ever come. One, and two, I'm not sure that's a big um, valuable use case. Like if I'm Amazon, I have to sit there and wonder, okay, let's see, if I'm spending, $500 million a year on logistics, or I don't know, $1 billion a year on logistics. I have this number actually. That's sort of savable. Like my orchestration of it is only a part of it, right? I actually still do have to pay people to move things, but let's say I can make it a little bit more efficient. I have an Amazon model here. And keep in mind this is the biggest company in the world. Fulfillment's 54 billion for Amazon in 2030. Right now it's 40 billion. Let's say they can make that 10% more efficient. That's $5 billion they can save. Quantum computer is something they could build themselves theoretically, and the market's not infinitesimal, but again, assuming that all these technologies come together such that they could do it, it's just one thing that'll assist in optimization. They already clearly do optimization. Um, it'd be good due diligence to ask some of these optimization experts, where do you see this playing a role, if ever? But I think that the biggest bang for the buck is 5 billion. Obviously, Amazon's not going to do it for 5 billion. They want a return on it, so maybe they do it for 100 million or 500 million. But they're not going to do it for. They're not going to pay 5 billion to save 5 billion. And the competitiveness of like silicon getting better, is something to not forget. I think in 30 years, whether it's probabilistic computing or just NVIDIA and their pathway, I'm not sure that even when we get there for quantum, that delta is going to be 5 or 10%. It may shrink to nothing. And, I wouldn't trust the future that much because we don't know what's going to happen. And NVIDIA is not stopping, right? They're accelerating. They're still going to be here. We can get the answers to these problems really, really easily. So I feel like, it's sort of a lot to bet on because, we haven't seen that speed up. And I feel like, until somebody from Amazon says we can save billions of dollars this way, and so can every other shipping company, it still would be an overvalued sector because, like, as I mentioned, the amount of money spent on logistics and the amount amenable to savings, like maybe you could get a little bit more efficiency out of a worker, but you're still paying that worker. So the route's a little more efficient, perhaps, but they are doing that now. One, and two, like, you know, shaving a few seconds here and there will, it does add up, but I still feel like there's, minimal upside here, just because.
I think I've heard you talk about like cryptography regarding quantum and cracking RSA, maybe ECC, maybe factoring discrete logs. So it's there. I'm hearing that it can be very useful for cryptography, but you think we're anywhere near maybe 10 years down the line from cracking these sort of things, or is it just like we are so distant and we're you can put only so much information in a quantum computer, it can't really handle these bigger problems yet?
Yeah, I mean, so for factoring, the amount of information is very little. right? And that's what makes factoring so cool is that it's a 300 digit number, but if you were to try to factor it, it would take you till the end of time to do it, which is really neat. That if you wrote that number down beforehand, you say, "Oh, well, here's the answer. I had it all along," and it's basically nature's password, which is really really cool mathematically and scientifically. But so quantum computers don't need that much information. As I just said, 1,000 bits will give you the world record factoring problem. So you don't need, you know, a lot of qubits. We already have 150 qubit machines in IBM's cloud. The thing that you do need is getting high fidelity, so you can actually run the experiment. But I think those problems will start to get solved. There is an outside chance that it just can't get solved. There are some people that think that. I'm not in that camp. I'm an optimist. um, as crazy as that sounds to some people, like I am an intrinsic optimist, but I'm not a fool. Um, so I believe that we will be able to control matter and harness quantum effects to do calculations. But the complexity speed up is really important here. To go from the exponential class of problems to the polynomial class of problems. Polynomial time is tractable, exponential time is not. So that complexity shift is really important. And the only class of problems that has proven complexity shift is Shor's, which is the integer factoring in essence. So integer factoring is not useful to anybody other than code breakers, hackers, maybe nation states. But I can't see for sure, right? But with sustained investment, meaning quantum doesn't go cold again because it's had the cold hot cycles. It's been around 2 cycles now of winter and spring, and we're clearly in spring right now. But I assume we'll get to winter again soon. Um, I see if you assume just sustained investment nonstop without the breaks, I could see in 10 years we could crack state of the art Shor's, and that's a big thing. Shor's been around 50 years. GCHQ, which is the UK NSA, had Shor's before Shor. I'm sorry, had Shor's before RSA. RSA, Rivets, Shamir, and Edelman. They published their groundbreaking RSA paper. I think it was 1979. But the hackers and spies in Britain, the Brits had it in 1975. So the obvious thought here is that these weren't independently discovered. There were whispers about this, and they made it to MIT, and MIT professors, quote unquote, invented this. Just a funny backstory about it. It doesn't matter that much. But RSA has stood tall for 50 years. Now, by the way, you can make key sizes bigger. There's a bit of a pain in the ass that occurs, but we're on 2048 bits. So 2048 bits are big. That's double. That's like a 600 digit number. So if we go to 4096 or 8,000 bits or something, you can even outrun a quantum computer. And then, of course, lattice-based cryptography is already getting standardized out there. It should be as simple as a pip install, npm install package at some point. So I could see very, very soon, people start to implement lattice-based because it should be as simple as implementing RSA. So I think that, everything will be fine. Bitcoin will have to go through some interesting transitions, but the death of RSA is not that crazy. AES kind of died. So, these things do happen. And, there's a first time for everything. Technology is by definition the first time. So RSA will have to disappear, I do think, but I'd be surprised if it happened in the next 5 years. I would not be that surprised if it happened in 10 years, but I also wouldn't be surprised if it happened in 15 or 20 years due to the nature of funding cycles. We're at an all-time high of funding. Mostly it's going to AI, but we're at a really, really large funding kind of peak that may dissipate for many years. And in those years, companies hunker down. They don't really do much research, especially smaller companies. Google and IBM may be undeterred, but your smaller companies are wondering how they'll survive. Eventually, winter will thaw, but you can spend 5 years in winter and lose 5 years of progress. So I would not be surprised if it happened in 10, but I also would not be surprised if it happened in 15 or 20, but there was just dead time in there. Um, so, and again, you have to ask yourself, what's the big payoff here? You know, splitting a number into two is not that exciting. Nobody's job relies on that. So anyway, that's how I feel about quantum. Anybody else? INMB. Let's maybe try to talk about. And thanks for calling.
Yeah, thanks. Thanks.
Where are my INMB fans? Where are you at? I know it's embarrassing because, like, if you're not a professional investor,
I
you
mean,
could
while we
feel.
wait, just one thing I do want to point out. Um, a huge bear case for quantum could be that, why would Nvidia spend, multi-billions of dollars on, GPU and these huge data centers if quantum computing is such a risk or such a threat? Like, you wouldn't spend billions of dollars on huge infrastructure projects just to be wiped out in 10 years. Like, it just doesn't make sense. But the reason why I bring up my previous points is just because of, things that I've heard and things that I'm just doing my own research as to like the possibilities of it being used. But what are your thoughts? Like, do you think that's like something that's a valid point, or do you think I'm just looking at it from the wrong angle?
Yeah, I don't think it's a valid point because we all know and can think of examples of companies that put their head in the sand and just avoided technological change that said, oh, that'll never work. And pharma said that about antibodies. They looked at these antibodies and they said, wait a second, you're telling me I have to create a microbial system that's alive, that spits out these drugs in this goop. Then you want me to go in the goop, filter it out, and then you want me to give it by IV because you can't do it orally because it's a protein. You want me to give it IV to a patient. It can't go intracellular. It can't cross the blood-brain barrier, but somehow this is going to be useful as a medicine. I mean, Pfizer and Merck said, well, you got to be fucking kidding me, right? Anything you guys could do, we could do with small molecules. Now, they were wrong. They didn't adapt, they didn't change. They had to be mentally flexible. And it's just something that forced them to become left behind. So technology is full of stories like this where, people have just, forgotten to advance with time. I don't think NVIDIA is one of these companies. I think NVIDIA is a company that is very smart and they're going to figure out what to do with quantum, if anything. But I also think that it's not it's not beyond the pale. It's not impossible that NVIDIA simply just does nothing and makes a mistake, whether it's quantum, probabilistic, DNA computing, it could be anything. So I wouldn't just rest on NVIDIA's so smart, they're doing nothing, therefore it's nothing. Microsoft missed AI, and rapidly caught up, but Apple completely missed AI, and they're smart. But so there's a number of cases in technology where it's just you can't just say these guys are so good that how could they miss it? Now, obviously, I think it's fair to say that like most of tech is not that excited about quantum. The IBM effort and the um, Google effort, and certainly a little bit the Microsoft effort. They're semi-serious. They're kind of side projects for those management teams. They look at it for a small period of time, maybe once a year, and then for focus on their main business. But you know, that's why they're moonshots, and most of these moonshots don't come. Nothing sort of comes of it. It'd be fascinating to me if IBM, you know, broke out quantum revenue, started talking about it every call, and was really fixated on it. But I think that it's really just a sideshow, and most management schools will tell you these days to avoid sideshows. And I'd be surprised if at some point Google or IBM kicks quantum to the curb. Google is now trying to figure out how they stay relevant in the world of AI. They're very good at AI, but they also are not very good at executing. So I think for Google, it's a distraction, but they silo it good enough that it doesn't distract management. I think management doesn't even know what the fuck's going on in quantum.
And just to follow it up, if you were speaking to like your typical like quantum investor, whatever, like person that just downloaded Robinhood and is tossing, their $50 whatever allowance or whatever into this. Like, if you can explain in a few sentences to that person why quantum does not have a future in very like layman's terms, what would you say to this person without having them to, sit down and listen to like a full 40-minute conversation? What would be your main driving point?
Yeah, so I've done this in the Shea interview, but basically quantum is a distant technology that solves a very narrow use case. The narrow use case is the set of algorithms that are speed ups in complexity classes from largely from exponential to polynomial. Running an algorithm in polynomial time is vastly preferential to running an algorithm in exponential time. Quantum effects allow you to do that by taking advantage of things like entanglement and superposition. But unfortunately, the only known quantum algorithms which take you from exponential time to polynomial time are Shor's algorithm. Shor's algorithm is only relevant for factoring. There's other algorithms, but their speedups are much, much less. Between the distant time it's going to take for quantum to come alive and the very narrow space of computing that it can do, for example, it cannot do AI, it cannot do anything with large amounts of data. It can only do this really, really narrow space of problems. You'd have to be confident that either there's going to be more problems that can be solved, but if you read the literature, there's not much hope. The last major quantum algorithm that was discovered was 25 years ago. There's not much hope that there's going to be another one. Um, in fact, Shor's discovery, which was a stroke of genius, um, basically created the need for quantum computers. Without Shor, there never would have been an interest in making quantum computers at all. And so we don't know if we're going to see another Shor's algorithm. We might, but it could be a cold 25 more years before you see that. And so if you don't think there's going to be a new complexity class shift for a problem of significance, and I would argue most NP hard problems are honestly not problems of significance. But regardless, if you think that, one, you should say, well, what is it, and why do you think there'll be a complexity speed up, and then why is this NP hard problem so important? And two, how much revenues are going to be from this NP hard problem? Because if you look at again AI, this isn't sort of a quantum problem. AI is basically the only computationally difficult problem at the moment, and AI suffers from both large scale of computations in parallel, as well as large amounts of data. The problem with AI is that the RAM size of these chips is really small, and if you spoon feeding it across all the chips is a really difficult problem. Where the fabric is actually, almost as valuable as the GPU. So there's a bit of that, dynamic going on where, you know, the problem in AI isn't just I need more machines. It's kind of actually I need bigger machines that have better bandwidth. They're calculating quite quickly. It's actually a lot of it's the data in transit that's rather difficult. So in any event, we'll see if NVIDIA can scale and techniques can scale, and we may not have a computing problem in as soon as a year or two or a few years where what's left to compute. Right now, computing AI is largely the only large scale computing problem that's really difficult. You could add weather simulation in there or something, but there's very few problems that really require fields and fields of computers. And so that problem will probably be solved before quantum can even, factor a small number. So that's kind of the way I look at it. Let's try to move on to another caller. I appreciate your time though.
Hey Martin, I was just wondering if you had considered that companies like QBTS could maybe be able to push their offerings to other research institutes like Jülich to um, gain more market share and more revenues in the short term. Like, for example, if they were be able to find like two other research institutes in the world that would have some motivation to do science where QBTS has been proven to be successful, like with vacuum decay in physics. So they would maybe acquire more machines, and that would lead to a short-term increase in qubits for the moment.
Yeah, so I think that, obviously Ulick buying a machine is a bullish thing for D-Wave. But I think if you think about, peeling back the layers of kind of like why did they do it and when the last time is that anybody bought a D-Wave machine, they sell them every 5 years. So it would be very surprising if all of a sudden they sold several this year. And management didn't sound too, excited about that. But I think that the people I've talked to in Germany have said that Ulick had a budget and their budget flush where they were under budget. They basically needed to spend money on something. So they're willing to buy the D-Wave computer. Um, I think it's more indicative that this is a one-off, but certainly I would applaud management if they can get a second customer. Now, Ulick having one of these machines is also willing to rent them out to others, including at no cost. So, there is something to be said for, kind of, you know, selling this machine kind of increases the world's capacity of this machine. And, Ulick as an academic center is very willing to work with other academic centers. So I'm not sure other people will see the FOMO and say, we need one too. If curious, I think they sort of talk to Ulick and say, well, what are you doing with it, et cetera, et cetera. And they may borrow it, but, I wouldn't count out the possibility that somebody else buys it. But I really feel like given the cloud opportunity, you can use D-Wave on the cloud. There's no need to actually own a machine if you can rent it for $5,000. Why pay 15 million? So I feel like that's fairly I'm fairly comfortable that they won't see another big purchase soon. But again, even if they do, $15 million sale, wonderful. But you need dozens of those or hundreds of those for the market cap to make sense.
Maybe to counter that in the short term, like if we look at the study that has been done on the Ulick machine concerning vacuum decay, it is quite evident that it has taken quite a lot of time for the machine to be configured in the right way to actually have the computations make sense. So therefore, it could reasonably be thought that there might be a bottleneck in terms of the time it takes to configure the machine versus the time it then actually takes to run the experiments and make good science there. So that's why I also think that the D-Wave machine might also not be that relevant for commercial customers, right? So their market valuation might be a bit high.
Yeah, I think so too, obviously. And we'll see. I mean, I feel like, you know, the nice thing about the stock market is every quarter you get a little update that says how much money they made or lost, and we'll know in 30 days or so, uh, 90 days, 60 days, something like that. Okay.
I think it's very unlikely that any customer will come up in the next quarter or two, right? There would be a need for good science by Ulick, and also the inability of Ulick to serve a further demand for research on their machine to actually make D-Wave make another sale, right?
Yeah, I mean, we've already seen them rent some machines out, so it'll be interesting to see, um, you know, uh, see them see somebody else use it, get jealous or something like that, and say, "I want this myself." I mean, $15 million is not does not grow on trees. It is definitely a lot of money to spend. There are very few places that just throw $15 million away without thinking about it. And I think even if you were interested in this, obviously, it might make sense to rent or try or partner with Ulick. I mean, they spent the 15 million, so why not partner with them? And they've said this, right? They've said like, come to our Ulick Computing Center, right? Like, there's no reason to go anywhere else when we have one all set up. we're pros at using it. We're academics, so we'll partner with you. Just write
Mm,
research together. So it'll
sorry,
be
from what I understand, Julik's new research grant also involves researching the feasibility of different quantum computing systems and their limitations and possibilities. So they have quite a high motivation to actually get someone to use their system now that they paid for it, right?
yeah. I think that's right, and I think that we're going to also um, see them stay active in other areas. I do think it's smart for Germany to stay on top of this stuff. It is it seems like a lot of money being wasted, but at the end of the day, $1 billion a year to stay at the forefront of computing is probably smart. We should probably do that too, quite frankly, here. We rely on our universities to do that. So lots of universities in America have large clusters of GPUs, but they certainly don't do much on the quantum side. And I think the D-Wave CEO as much said that. He said basically in the US, nobody believes in annealers, but in the rest of the world, we get a little traction. So we'll see. I mean, I certainly want to try it. So if I want to try it, maybe somebody else does too.
Yeah, that might be right. But also, I think Germany, because of some other research projects they let fall behind, have an inherently higher motivation to stay on the front of the things they might reasonably able to stay in front of. So yeah, I think that's the reason the money is going there, because it might work out, and if it works out, it's quite a good deal. So yeah. But thanks for your time and your thoughts, Martin. Have a good one.
Well, thank you. Any immune bulls? Immune.